Welcome to Lecture 3 of our flow matching course, Probability Paths, Designing the Journey. In Lecture 1, we built intuition about generative models using physical analogies, wind maps, moving sand, and our running example of transforming a Gaussian cloud into the two moons shape. In Lecture 2, we formalized that intuition with ODEs and neural ODEs. We saw how a velocity field defines a flow, and how that flow transforms distributions via push forwards and the continuity equation. But we ended Lecture 2 with a problem. Training neural ODEs requires solving an ODE at every training step, which is prohibitively expensive. Today we take the first step towards solving that problem. We will learn how to design probability paths, the journey from noise to data, in a way that will unlock simulation-free training in Lecture 4. The mathematics today steps up to undergraduate probability, conditional distributions, expectations, and marginalization. But as always, we will build the intuition first. Let us quickly recall where we are in the course. In Lectures 1 and 2, we established the core framework. A velocity field ut defines a flow psi c through the ODE. That flow pushes the source distribution, noise, toward the target distribution, data. The continuity equation tells us how the density evolves as the velocity field moves probability mass around, and neural ODEs let a neural network parameterize the velocity field. But we hit a wall. Training a neural ODE requires actually solving the ODE at every gradient step, which means 50 to 200 forward passes through the network per training iteration. That is impractical for anything beyond toy problems. So today's question is, can we design the path from noise to data in a clever way that sidesteps this bottleneck? The answer is yes, and the key idea is to work with probability paths that we can write down explicitly without ever needing to solve an ODE to construct them. On the right, you can see our course roadmap. We are at Lecture 3, about to tackle probability paths. This lecture sets up all the ingredients. Lecture 4 will show how to turn them into a training algorithm. Let us set up the problem precisely. We have two distributions. On the left is the source distribution P, which we choose to be something simple and easy to sample from. The standard choice is a Gaussian. X0 is drawn from a normal distribution with mean 0 and identity covariance. This is our noise. On the right is the target distribution Q. This is the data we want to generate. In our running example, it is the two moons shape. In a real application, it might be the distribution of natural images, or protein structures, or audio waveforms. We do not know the density of Q explicitly, we only have samples from it in the form of a training dataset. The generative modeling problem is, given a way to sample noise from P, find a transformation that converts those noise samples into data samples from Q. The big question mark in the middle of this slide is what this lecture is about. How do we connect P and Q? In Lecture 2, we saw that flows and ODEs provide one answer, but we need a smarter way to set up the problem. That smarter way is the probability path. Here's the central concept of today's lecture. The probability path. A probability path is a continuous family of distributions PT parameterized by time t running from 0 to 1. At time 0, Pt equals P, the source distribution, our Gaussian noise. At time 1, Pt equals Q, the target distribution, our data. For times in between, Pt is some interpolation between these two extremes. Notice that each Pt is a full probability distribution over Rd. It is not a single point or a single sample, it is an entire distribution, a density function that tells you the probability of finding a sample at any location in space, at that particular moment in time. A helpful analogy is a crossfade between two songs. At the start, you hear only the first song, at the end, only the second, and in between, you hear a blend. A probability path is the same idea, but for distributions instead of audio signals. On the right side of the slide, I have sketched what this looks like in one dimension. At t equals 0, we have a single Gaussian bump. At t equals 1/2, the distribution is starting to split into two modes. At t equals 1, we have the bimodal target. the distribution smoothly morphs from one shape to the other. Think of the probability path as a movie. Each frame of the film strip on this slide is a snapshot of the distribution at a particular time. At t equals 0, the first frame, we see a random cloud of noise. As t increases, the points start organizing themselves. By t equals 0.6, you can begin to see the two crescent shapes emerging. At t equals 1, the final frame, we have clean 2 moons data. This movie metaphor is important because it tells us exactly what a probability path is. A continuous sequence of distributions, one for each time t. Not just the start and the end, but every frame in between. Why do we need the full movie and not just the endpoints? Because the velocity field ut, the thing we want our neural network to learn, depends on where the distribution is at each moment in time. If we only knew p0 and p1, we would not have enough information to define ut at intermediate times. The probability path is what gives us a training signal. At any time t, we can say where samples should be and what direction they should be moving. The question now becomes, how do we construct this movie? How do we choose a good probability path? That is what the rest of this lecture addresses. Now comes the key insight of flow matching, and honestly, one of the most elegant ideas in modern generative modeling. Constructing a probability path for the entire target distribution Q is hard. If Q is the distribution of all natural images, or all protein structures, we are talking about an incredibly complex, high-dimensional distribution. Designing a smooth path from a Gaussian to that distribution is a daunting task. But what if we simplify the problem? What if, instead of trying to move noise toward the entire target distribution at once, we focus on moving noise toward a single data point x1? This is much easier. Moving a cloud of Gaussian noise to a single point is a well-understood problem. We just need each noise particle to drift toward that point. The conditional strategy works as follows. First, pick one data point x1 from your training set. Second, design a path that moves noise toward that specific x1. Third, repeat this for every data point in the dataset. Fourth, combine all of these conditional paths to recover the full path from noise to the target distribution. This is a classic divide and conquer approach. One hard problem becomes many easy problems. On the right side of the slide, you can see the picture. Many noise particles are all converging toward a single highlighted data point, while the other data points are faded in the background. Let us now give this conditional path a precise definition. We write pt given x1 for the conditional probability path. This is the distribution of sample positions at time t, given that they are all heading toward the data point x1. The boundary conditions tell us what happens at the two endpoints. At t equals 0, the conditional path equals p of x, the source distribution. Every sample starts as noise regardless of which data point it is heading toward. This makes sense. At the very beginning, we have not started moving yet, so the distribution is just the noise distribution. At t equals 1, the conditional path collapses to a delta function at x1. This is a distribution that concentrates all its probability mass at the single point x1. In other words, by time 1, every sample that was heading to x1 has arrived exactly at x1. On the right side of the slide, you can see this visually. At the top, t equals 0, we have a wide Gaussian. In the middle, at t equals 1/2, the distribution has narrowed and shifted toward x1. At the bottom, t equals 1, it has collapsed to a spike, the delta function at x1. The conditional path is like a funnel. It starts wide and narrows to a point. The question is, what specific shape should this funnel take? Now we make a concrete choice. The simplest possible conditional path is a straight line. The formula is mc of x0 given x1 equals 1 minus t times x0 plus t times x1. That is it, a linear interpolation. Let me unpack this. x0 is a noise sample drawn from the source distribution P, x1 is a data point from the target distribution Q, xt is where the sample finds itself at time t. The formula says, xt is just a weighted average of the noise sample and the data point, where the weight gradually shifts from x0 to x1 as time goes from 0 to 1. At time 0, the weight on x0 is 1 and the weight on x1 is 0, so xt equals x0. Pure noise. At time 1/2, both weights are 1/2, so xt is the midpoint between noise and data. At time 1, xt equals x1. The sample has arrived at the data point. Look at the diagram on the right. Several noise points, shown in orange on the left, are connected by straight lines to a single data point, x1, shown in green on the right. The purple dots mark the midpoints at t equals 1/2. Every sample travels in a straight line from its starting noise position to the same destination, x1. This is as simple as a path can be. And remarkably, this simple choice turns out to be not just adequate, but in some sense optimal, as we will see shortly. Now here is something beautiful. If the path is a straight line, what is the velocity? We just differentiate. The derivative of 1 minus t times x0 plus t times x1 with respect to t gives us negative x0 plus x1, which is x1 minus x0. That is the entire conditional velocity field, x1 minus x0, the direction from the noise sample to the data point. And notice something remarkable. This velocity does not depend on t at all. It is constant in time. The sample moves at constant speed in a straight line from noise to data. Look at the diagram on the right. Along the dashed line from x0 to x1, I have drawn velocity arrows at several points. Every arrow points in the same direction and has the same length. The velocity is the displacement vector from x0 to x1, and it is the same at every point along the path. This is important for a practical reason. When we get to training in Lecture 4, the neural network will need to predict this velocity, and what we are asking it to predict is simply the vector from x0 to x1. No complicated time-dependent formula. No ODE to solve. Just a direction. This is the training target. Given a noisy sample xt at some time t, predict x1 minus x0. That is what flow matching training boils down to. So far, we have focused on the path from noise to a single data point, x1. But our target distribution Q has many data points, not just one. What happens when we consider all of them? Look at this slide. On the left, we have several noise samples. On the right, we have several data points arranged in the two moons pattern. Each noise sample is connected to a data point by a straight line. That is one conditional path. We have 5 paths shown here, each heading to a different data point. At time t equals 1/2, each sample is at the midpoint of its respective line. The purple dots show these intermediate positions. The red arrows show the conditional velocity for each sample at that moment. Each arrow points from the sample's current position toward its destination. Now, here is the challenge. Each conditional path has its own velocity field. The velocity of a sample heading to one data point is different from the velocity of a sample heading to a different data point. But ultimately, we want to train a single neural network that predicts a single velocity field ut of x. One velocity for each position x, not one per data point. How do we combine all these conditional velocity fields into one marginal velocity field? That is the question at the bottom of the slide, and it is exactly what the marginalization trick answers. This is the marginalization trick, the conceptual heart of flow matching. Today I will state it informally. The rigorous version comes in Lecture 4. The marginal probability path, pt of x, is obtained by averaging the conditional paths over all data points. The formula says, integrate pt given x1 times q of x1 over all x1. In words, take the conditional path for each possible data point, weight it by how likely that data point is under q, and add them up. The marginal velocity field ut of x works similarly. It is the conditional expectation of the conditional velocity ut of x given x1 conditioned on xt equals x. In plain language, the marginal velocity at position x is a weighted average of all the conditional velocities, one for each data point x1, where the weights reflect how likely each x1 is to be the destination of a sample currently at position x. The diagram on the right illustrates this. The purple dot at the center is a sample at position x at some time t. 3 data points are shown around it, each pulling the sample in a slightly different direction. The thin arrows are the individual conditional velocities. The thick red arrow is their weighted average, the marginal velocity ut of x. The marginalization trick states, if each conditional velocity field generates its respective conditional path, then the marginal velocity field generates the marginal path. This is the mathematical guarantee that the divide and conquer strategy works. Designing easy conditional paths individually is equivalent to designing the hard marginal path. We will prove this formally in Lecture 4. For now, the key takeaway is, we never need to compute the marginal velocity directly. We only work with conditional velocities. Let me summarize why this conditional approach is so powerful. On the left side of the slide, we have the conditional world. Everything is easy here. The conditional flow is a straight line. Psi t equals 1 minus t times x0 plus t times x1. The conditional velocity is x1 minus x0. Both are in closed form. No integrals, no ODEs, no approximations. On the right side is the marginal world. The marginal velocity ut of x is a conditional expectation. It requires integrating over the entire data distribution Q. This is intractable. We cannot compute it in practice because Q is only known through finite samples. But here's the punchline. We never need to compute the marginal velocity. We design in the conditional world. We train in the conditional world. The only thing we need from the marginal world is the guarantee that it is consistent, that the conditional approach gives the right answer, and that guarantee is exactly what the marginalization trick provides. Think of it this way. To train the network, all we need to do is sample a noise vector x0, sample a data point x1, form the interpolation xt at a random time t, and ask the network to predict x1 minus x0. That is the entire training procedure. We never compute pt, we never compute ut. We only use conditional quantities which are trivially available. The mathematics guarantees that a network trained this way will learn the correct marginal velocity field. We will see the formal proof in Lecture 4. Let us now generalize the linear path to a broader and very practical family, Gaussian paths. With Gaussian paths, the conditional distribution at time t, given destination x1, is a Gaussian centered at alpha t times x1 with variance sigma t squared times the identity matrix. The mean drifts toward x1 as t increases, and the variance shrinks toward 0. The underlying conditional flow has the affine form. Psi t of x0 given x1 equals alpha t times x1 plus sigma t times x0. This is a simple weighted combination of the data point and the noise, governed by 2 functions of time, alpha t and sigma t. We call this pair a scheduler. The scheduler must satisfy boundary conditions. Alpha goes from 0 to 1, meaning the data component grows from nothing to full weight. Sigma goes from 1 to 0, meaning the noise component shrinks from full weight to nothing. Alpha must be increasing and sigma must be decreasing. The table on the right shows 3 common schedulers. The Kondo T scheduler sets alpha t equals t and sigma t equals 1 minus t. This is exactly the linear path we already discussed. The VP linear scheduler uses sigma t equals the square root of 1 minus t squared, which preserves the variance throughout the path. The cosine scheduler uses trigonometric functions for a smoother transition. The key insight is that all Gaussian paths share the same structure. The only design choice is the scheduler. Once you pick alpha t and sigma t, everything else, the conditional flow, the conditional velocity, and the training procedure, follows automatically. We have seen that straight lines are the simplest choice, but are they also the best? It turns out they are, in a precise sense. The linear conditional path minimizes a bound on the kinetic energy, the integral over time of the expected squared velocity. Less kinetic energy means the velocity field is simpler, lower magnitude, less variation over time. And a simpler velocity field is easier for an ODE solver to follow, which means fewer steps are needed at inference time. In fact, for a single target point x1, the linear path is exactly the optimal transport solution. It is the path that moves probability mass from the source to the target with the least total effort. The velocity is constant, the acceleration is zero, and a single Euler step recovers x1 exactly from x0. Compare the two paths on the right side of the slide. The top path, in green, is the OT path, a straight line from noise to data. One Euler step gets you there. The bottom path, in red, is a curved alternative that makes a detour. It arrives at the same destination, but the ODE solver needs many intermediate steps to follow the curve accurately. The table quantifies this. The OT path has constant velocity, zero curvature, and needs roughly one Euler step. The curved path has varying velocity, non-Norrie curvature, and needs 50 to 100 steps. In practice, this difference translates directly to sampling speed. OT paths enable fast generation with very few neural network evaluations. This is why the linear conditional OT path is the default choice in most flow matching implementations. It is simple, principled, and efficient. Let me recap what we have accomplished today and what remains. We established 7 key ideas. First, the generative modeling problem is about connecting a source distribution P to a target distribution Q. Second, we connect them with a probability path PT that interpolates from noise to data. Third, we build this path using conditional paths, one per data point. Fourth, the simplest conditional path is a linear interpolation. xt equals 1 minus t times x0 plus t times x1. Fifth, the corresponding conditional velocity is simply x1 minus x0. Sixth, the marginalization trick guarantees that combining conditional paths recovers the correct marginal path. Seventh, Gaussian paths provide a flexible family parameterized by schedulers, with the OT path being the kinetic energy minimizing choice that enables fast inference. But there is a critical piece still missing. We know what paths to design and what velocity to target, but we have not said how to actually train a neural network to learn the velocity field. What loss function do we use? Why does minimizing it give us the right answer? And what is the formal proof that the marginalization trick works? All of this comes in Lecture 4, Flow Matching, the training algorithm. We will see that training amounts to simple regression, with no ODE simulation required. The loss function is just the squared error between the network's prediction and the conditional velocity x1 minus x0. And we will prove formally that this is equivalent to matching the marginal velocity. Thank you. See you in Lecture 4.